let's define our definite integral. So we have the integral of f of x dx from a to b, which is equal to capital F of x evaluated from a to b, which is equal to capital F of b minus capital F of a, where capital F of x is the integral of f of x, and f of b is the value of the integral at the upper limit, where x is equal to b, and f of a is the value of the integral at the lower limit, where x is equal to a. And for definite integral, you have to keep in mind certain properties in order to make your calculations easier. First, we have the integral of a constant. We have the integral of c dx, where c is any constant from a to b, is just equal to c times the quantity b minus a. When we apply definite integral, c dx becomes c times x. Then we evaluate that from a to b, giving us c times b minus c times a. And we can factor out c, giving us c times b minus a. So this states that the integral of a constant function f of x is equal to c is just the constant times the length of that interval. So here we have the integral of 5 dx from 2 to 4. So our function is f of x is equal to 5. So here we have 5. And getting the definite integral is just the same as getting the area under that curve or that function. So we have from 2 to 4. So what we are essentially getting when doing definite integrals is getting the area of this shaded region. So the length of this area is 2 and the height is 5. So what we should get after doing the definite integral is 5 times 2, or just equal to 10. So let's proceed with applying definite integral. So what we have to do is to just integrate. So 5 dx becomes 5x evaluated from 2 to 4. So we get 5 times 4 minus 5 times 2. 5 times 4 is 20 and 5 times 2 is 10. So simplifying, what we get is 10, which matches with the area under this function. So that's the first property, which is the integral of a constant. Next, we have the constant multiple rule. So we have the integral of c times the function f of x dx from a to b, which is equal to c times the integral of f of x dx from a to b, where c is any constant. So this property states that the integral of a constant times a function is the constant times the integral of the function, meaning we can take out that constant in front of the integral sign and we will still get the same answer. So let's try that with an example. So here we have 3x squared. First, let us evaluate this integral as it is. So we get 3x squared plus 1. So divided by 2 plus 1. We get 3x cubed over 3. 3 on the numerator and the denominator cancels out, giving us x cubed. What if we brought 3 or the constant in front of the integral. So we have 3 times the integral of x squared. Integrating this gives us x cubed over 3. Then we multiply it by 3 since we brought that out. So again, 3 cancels out, giving us x cubed. So here, we can take out the constant in order to make the operations much simpler and still get the same answer. Let's try with another example. We have 3x squared plus 3x. So let us first integrate as it is. So we have integrating 3x squared, we have x cubed from our previous example plus 3x squared divided by the new exponent 2. So we have x cubed plus 3 halves x squared. So what happens if we bring out 3? So we will get 3 times the integral of x squared plus x. So integrating this gives us 3 times x cubed over 3 plus x squared over 2. So distributing 3, we get 3 over 3 x cubed plus 3 halves x squared. So this one cancels. And we end up with x cubed plus 3 halves x squared. So we get the same answer whether we bring out the constant or not. So keep in mind that we can only bring out the constant. And if you also bring out x or whatever variable that you can factor in front of the integral sign, we will not get the same answer. So we will end up with an incorrect answer. For example, we can factor out 3x here. So we have 3x times the integral of x plus 1 dx. So integrating, we get x squared over 2 plus x. And multiplying by 3x, we get 3x cubed over 2 plus 3x squared, which is very far from the correct answer. So keep in mind that what you can only bring out is just the constant and not the variables. Next property, we have the sum rule, which states that the integral of a sum is the sum of the integrals. So this is convenient when we are doing much harder integrals, such as integrals by partial fractions. So we can integrate each term separately or each function separately. For example, here we have x squared plus 2x dx. So let's just integrate as it is. So we have x cubed over 3 plus x squared. Then evaluate this from 3 to 4. So what we get is 4 cubed divided by 3 plus 4 squared minus 3 cubed divided by 3 plus 3 squared. So this gives us 64 divided by 3 plus 16 minus 27 over 3, which is 9 plus 9. So we have 112 divided by 3 minus 18. So let's set them up so that they have the same denominator so that we can subtract them from each other. So we have 112 divided by 3 minus 18 times 3 over 3. So this gives us 112 over 3 minus 54 over 3. So 112 minus 54 is equal to 58 divided by 3. So that's the simplest that we can factor it. So what we got integrating as it is 58 divided by 3. Now let's erase everything and integrate them separately and check if we can get the same answer, which is 58 over 3. So let's rewrite that and integrate separately. So we have the integral of x squared from 3 to 4 plus the integral of 2x from 3 to 4. So this gives us x cubed over 3 from 3 to 4 plus x squared from 3 to 4 as well. So this gives us 64 divided by 3 minus 27 over 3, which is 9, plus x squared when x is equal to 4, which is equal to 16, minus x squared when x is equal to 3, which is equal to 9. Simplifying this gives us 64 divided by 3 plus 16 minus 18. So multiplying everything by 3, we have 64 divided by 3 plus 16 times 3 over 3 minus 18 times 3 over 3. So we have 64 divided by 3 plus 48 divided by 3 minus 54 divided by 3. So 64 plus 48 is 112 minus 54. We have the same answer, which is equal to 58 over 3. So again, this may appear harder since we're just doing simple examples, but when we reach integration by partial fractions, this sum rule will be a lot more useful. Next, we have the difference rule, which is just the same with the sum rule. We just invert the operation from addition to subtraction, but they are essentially the same. So this property states that the integral of a difference is the difference of the integrals. Let's do the same example, but this time let's just use subtraction. So first we have x cubed over 3 minus x squared evaluated from 3 to 4. So this gives us 4 cubed over 3 minus 4 squared minus 3 cubed over 3 minus 3 squared. So these are still the same values. So we get 64 over 3 minus 16 minus the quantity 27 over 3 or 9 minus 9. So this just becomes 0. We are left with 64 over 3 minus 16. So we multiply this by 3 over 3 so that we can subtract them. So this becomes 64 divided by 3 minus 48 over 3. And 64 minus 48 is equal to 16. And copy the denominator, we end up with 16 over 3. So take note of this. And we are going to do the difference rule. So let me first clear all the writings. What we have is 16 over 3. Integrating them separately gives us x squared from 3 to 4 minus the integral of 2x from 3 to 4. So let's write here. This becomes x cubed over 3 evaluated from 3 to 4 minus x squared evaluated from 3 to 4. So let's substitute. We have x cubed over 3 when x is equal to 4 or just equal to 64 over 3 minus x cubed over 3 when x is equal to 3 or 27 over 3 giving us 9. Then we have x squared when x is equal to 4 giving us 16 minus x squared is equal to 9 when x is equal to 3. So this gives us 64 divided by 3 minus 9. Multiply it by 3 divided by 3 so that we can directly subtract them. Then minus 16 minus 9 or just 7. So 64 over 3 minus 9 times 3 which is 27 over 3 minus 7 times 3 is 21. So 21 over 3. Let's multiply this as well. So this now gives us 64 minus 27 minus 21. So we have 64 minus 27 minus 21. So 14 minus 7 is 7 minus 1 is 6. So this becomes 5. 5 minus 2 minus 2 is 1. So we have 16 and just copy the denominator 3, which is the same when integrating directly. Lastly, we have integrals of the same function over adjacent intervals. So symbolically, if we have the integral of a function f of x dx from a to c plus the integral of the function or the same function f of x dx from c to b, we can rewrite that, or that is just equal to the integral of f of x dx from a to b. So this is when a is less than c and c is less than b. So let's say we have a function f of x. So this can be any function. And we have our limits a, c, and b. So we know that definite integrals represent the areas under a curve. So the definite integral of f of x from a to c is just this shaded region. And the area, or the definite integral of f of x dx from c to b is just this shaded region in blue. So what this property tells us is that since they are the same function, instead of getting the areas under these two regions separately, we can get the definite integral directly from a to b and still get the same answer. Since they are the same functions and they are adjacent, when you add these two values or these two areas, the answer will be the same if you get this area as a whole. So we can manipulate this property algebraically when one of the three is missing. So that would be for our next example. So if it is known that the integral of f of x dx from 0 to 10 is equal to 17, and the integral of f of x dx from 0 to 8 is equal to 12, find the integral of f of x from 8 to 10. So here, let's just draw f of x as any curve since f of x can be any function. And let's write, or let's mark the interval. So we have from 0 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And from 0 to 8. So it is known that the integral of f of x dx from 0 to 10 is 17. So this whole region here is 17. And from 0 to 8, we have 12. So if this is 12, what must be the area of this region in order to get 17? So basically speaking, this area would be 5, since 5 plus 12 is equal to 17. Therefore, the integral of f of x dx from 8 to 10 is just equal to 5. And using the property and manipulating this algebraically, the integral of f of x dx from 0 to 8 is 12. The integral of f of x dx from 0 to 10 is 17. And we just copy this one. So plus the integral of f of x dx from 8 to 10 is equal to 17. So transposing 12 to the right side, we have the integral of f of x dx from 8 to 10 is equal to 17 minus 12. And 17 minus 12 is equal to 5. So this is our final answer. So that is all for this video. If you learned something, please leave a like. Or if you are having troubles with any of the topics discussed, leave a comment down below. In the next videos, I will be uploading more examples of definite integrals. And as always, I will see you on the next videos.